Quantum physics is, to put it simply, the study of how things behave when they aren't being measured. We know that, free of measurement, our world can act in bizarre ways. Importantly, unobserved objects can act entirely probabilistically, not being in one distinct state, but instead in many states at once, with varying probabilities of being in each of those states. This property, being in multiple states simultaneously, is known as superposition, and it's pretty neat, but it does bring up another question. We know that systems can only be in superposition when they aren't being measured, any sort of observation or measurement leading that superposition to collapse, the system now being in only one state. But to really understand this, we need to know, what exactly is measurement? Well, it'll also do with information. When any information about the state of a system escapes, a measurement has been made. Take this apple. Now, it's pretty clearly not doing anything too strange. All of its properties can be described with classical mechanics. So what's measuring it? What observation is keeping us from putting fruit into superposition? Well, for one, this apple is being constantly assailed by things like air molecules and photons, which, when they interact with the apple, bouncing off it and changing their velocity, carry information, like its position, out into the universe. Were we to follow each particle, we could use the changes caused by the apple's existence to piece together its properties, aka it's being measured. This is why quantum mechanics generally deals with objects like electrons or photons that are so small they aren't subject to this kind of measurement. Let's ignore all that though and pretend this is a quantum object, in a superposition of states, say, A and B. How can we get that superposition to collapse? Well, since we're imagining things, let's make up a special particle that, say, reflects off our apple when it's in state A, but goes straight through when it's in state B. So when we toss this particle at the apple, if it's in state A, the particle ends up over here after bouncing off. But if it's in state B, the particle goes straight through and ends up over here. So simply by observing where our particle goes, we can deduce the state of the apple. With our particle, information has escaped, and thus a measurement has been made. Not every interaction leads to measurement, however. We can see this by taking a new particle, one that bounces off the apple in both states A and B. When we throw this particle at the apple, no matter what state it's in, it ends up over here. Now, it's clearly interacting with the apple, it changes its course, but no matter what state the apple's in, it takes this path, so we can't look at this particle's position to determine whether the apple's in state A or B. It carries no information about the apple's state, so even though it's interacted with the apple, no measurement has been made. Now, it's also important to note that a measurement is made whenever information about the state of a system escapes, whether or not anyone knows it. As long as the state of the apple could be determined, regardless of whether we or anyone else are conscious of it, the superposition collapses. While this understanding of measurement helps us a lot, it's just a piece of a beautifully cryptic iceberg. We still have basically no idea what measurement actually does that causes superposition to collapse, or when exactly that collapse happens. Measurement is home to some of the most tantalizing mysteries of quantum mechanics, presenting a bountiful supply of confusion. What's not a mystery, though, is that quantum apples are pretty delicious.